is a p-n junction? Imagine this is a pure silicon lattice. This lattice doping, mixing with one side as to p-type, other side as to n-type. Then when this n-type and p-type meeting, there is a junction formed. It is called p-n junction. Now let's see what happened in this junction. We know there are free electrons, excess free electrons in the n side, and there are holes in the p side. So what will happen? Electrons jump to the holes. Then this electron recombine with the holes. So what will happen to the charge? Charge divided, chargeless. It becomes neutral. So it forms a charge divided area at this junction. As electrons leaving from this side, it becomes a positive charge. Holes align in the inside. And when electrons make a rich line in this p side, it creates a negative charge in the p side. A negative potential form, a positive potential form. Between these two, there is a barrier. As there are excess electrons in this line, these electrons oppose to flow of electron again and again from the inside. Now, this negative potential and the positive potential are divided by this area. So, they form a potential difference. This potential difference is called barrier potential. This area is called depletion area. Depletion region. This barrier potential difference for the silicon p-n junction is 0.7 volt. If it is a germanium lattice, it is 0.3 volt. To flow the current through this barrier in a silicon lattice, we have to supply an external voltage difference greater than 0.7. Now let us see what happens when a battery connects to this p-n junction. This battery can be connected in two ways. That is, connecting a battery is called biasing. Biasing the p-n junction. This biasing can be done in two ways. Number one, forward bias. The other one, reverse bias. Now let us see the forward bias. We know there is a depletion area. In the n side there is a positive potential. In the p side there is a negative potential. Connecting the p-n junction as the P side with the positive terminal of the cell and the N side with the negative terminal of the cell. So as this is the positive terminal, this is the negative terminal. Positive with P side, negative with N side. We know in this cell the negative potential is rich with electrons. So these electrons pushes these electrons in the negative side. So altogether electrons make a high potential V flow. So when the electrons flow in this side, the current flows to the opposite side. Current indicated by I. What happened to this depletion area? When these electrons in the cell pushes these electrons, depletion area become narrow. So the high negative potential overcome this barrier. So electrons flow, current also flow to the opposite direction. This type of connecting the cell is called forward biasing. Now let's see what happened. This cell is connected to the opposite side. Now I am going to connect the cell, the negative side to the positive and the positive side to the inside. Now I have connected this cell, negative potential to the P side, positive potential to the N side. What will happen? We know this positive potential attract the electrons in the inside. So what will happen? Electrons from this side move. So in this side, these holes increase this side. As electrons attracted by this positive potential, holes move to this side. At the same time, holes in this side attracted by this negative potential. This negative side also move to this side. So what will happen to this depletion area? Depletion area widen. So the barrier become bigger. Electrons cannot flow. So current also does not flow. I does not flow. This type of connecting the cell is called reversed bias. So we know when this PN junction connected forward biasly, we can make a current to flow, and in the reverse bias, the current does not flow. Okay, next to that, how we can use this PN junction